All right, how's it going, everybody? Albert here with AztecFec. We are the first team on San Diego State University's campus to build an AC to DC PFC boost converter power supply. Let me introduce the team to you. So going down the line, we've got Johnny, Armando, Charles, Ricardo, Ryan, Arash, and Omar. Now, purpose of power supplies, they're pretty much in all of our home appliances and all the appliances that we use on a day-to-day basis. But when we start getting into deeper high-power supplies, we're looking at electric vehicle car charging. We're looking at intricate lighting systems. We're looking at just a bunch of other things that we use that have DC in them. So to hit these higher voltage power supply specifications, we try to hit these performance targets. We're looking to plug it into a universal wall outlet. So that means voltage AC input being 90 to 264 volts and an input frequency between 47 and 63 hertz. We found that our typical input current around being 4.3 amps, and we wanted to hit a hold-up time of at least 10 milliseconds. Our output power ended up being 390 watts at full load with a regular continuous voltage output of 400 volts with a voltage ripple of 10 volts peak to peak. Now, of course, we also want to worry about efficiency, so we want our power factor to be at least over 0.95. And to talk a little bit more about that, here's Charles.
So to reach this high power factor that Albert just touched upon, our power factor correction controller is gonna focus on two things. One of them being high total harmonic distortion, and the other which leads to a poor power factor. So a visual of that is the waveform above, and as you can see, the input voltage is in blue and input current is in green. As you can see, the current is out of phase with reference to the input voltage and also highly distorted, causing poor power factor. An ideal, or our ideal input waveforms would look like the waveforms below. The input current being in pink and the input voltage being in blue. As you can see, the current is in phase with the voltage, and the signal is sinusoidal and has very little distortion, leading to a very high power factor. So how does our PFC supply do this? Well, first we need to look at a supply without active PFC elements. So first, you see this block diagram. AC signal is going to EMI filter, which is then being rectified to DC charging capacitor, and then supplied to load. This would be a typical waveform that you would see in the input for this sort of topology. This being input voltage and that being input current. As you can see, the input current is in phase with the input voltage, but it's still distorted, so causing a poor power factor. So to talk about how our PFC power supply is going to amend this problem, I'm going to pass it on to Armando.
How's it going, guys? So our design, in our design, we established a conventional power flow from left to right, and to include in our PFC power factor corrector design, we established switching power pole in the middle of the input and output stage. And this switching power pole specifically consists of a boost converter. This boost converter primary job is to raise an input voltage to an even higher output voltage. And this voltage is later going to be used as voltage sampling for the controller. That inductor right there in the boost PFC stage, that inductor, the primary purpose is to transfer energy from the input to the output. And it's going to do that only with the availability of having a bipositional switching, and that consists of a MOSFET as well as a diode. When the MOSFET is on, the energy will be stored in the inductor, and the diode is going to be off. When it's vice versa, that energy is going to be transferred to the output. This whole design was able to work successfully with the use of a controller. As you can see here, this is our end results, where we have an input voltage and an input current in phase with one another, and the power factor is obviously really good, and the distortion is pretty much gone in terms of the current. And to talk more about the controller, here's Ricardo Rivera.
Okay, so the main purpose of the PFC controller and power supply is to pulse width modulate the switch in the boost converter, which is a power MOSFET in our design. It uses feedback from the circuit to come up with the pulse width modulation duty cycle by reading the output voltage and comparing it to the desired voltage. It takes the error between the two signals and amplifies it with the voltage controller, and then compares that signal with the inductor current. The error between those two signals is amplified by the current controller to produce a control voltage, which is compared to a ramp signal. And those two signals produce the duty cycle for the MOSFET. For our design, we've chosen the Texas Instruments UCC28019A PFC controller. This is a full schematic showing the connectivity of the controller to our power supply. The controller here is in baby blue, and our full power supply schematic is laid out on top of it. In blue on the left, there is a resistor network which provides input protection for our power supply, including brownout protection as well as inrush overcurrent protection. The current protection also provides the template of the current, which gets compared to the voltage to produce the control voltage, which I mentioned in the previous slide. This resistor network on the right in the red, from the output of the power supply to the voltage sense pin of the controller, reads in the output voltage, and it uses that to determine the control logic within the controller to produce the duty cycle, which it's passed to the gate of the MOSFET with this orange lead here. The MOSFET is shown in purple, as well as the inductor and the main diode. The three components together are responsible for boosting out the output voltage to the desired value. To talk a little bit more about our design and some of the challenges faced with it, I'm going to pass it to Ryan to talk about the PCB.
All right, thank you, Ricardo. So as Albert mentioned, we are dealing with high voltages here, and one of our design constraints, as seen on the right, we have a basic PCB design as seen on Expedition PCB. We have a two-layer design. Pink will be the bottom, and blue is the top layer. And wherever you see anything filled in pink or blue is going to be just all copper related and traces. So in order to meet this design constraint, we had to deal with voltage breakdown and air dielectric. So for our 300 to 500 volt range, we had to have at least a minimum of 1/10 of an inch separation. Most of the PCBs here for robots and smaller PCBs, they don't have to worry about the separation as much as we do in order for us to prevent any current arcing over, voltage arcing over, causing a short within our circuit and possibly an explosion. So in order to compartmentalize everything in our circuit for our 5x5 inch PCB board, we had to segment the board into three main portions. We have our input 9264 volt AC input that goes into our EMI filter stage, which then is it's rectified through our bridge stage, which is then passed over to our output boost, which is works conjointly with our controller stage. We're just gonna get our desired output voltage of 390 volts and above. And with that, I'll pass it over to Omar, who's gonna explain more about his daughter board layout. As you can see on the left side of the screen, sticking up, our little daughter board is gonna control pretty much the frequency that's coming out to our main board.
All right, so as Ricardo mentioned earlier, the daughter board or the controller, the PFC chip itself is a crucial part to our design. Without it, our circuit will boost incoming voltage, but no power factor correction will take place. Making this board wasn't as challenging as creating the boost circuit board. However, getting them both to cooperate was a challenge. So we aimed for a small, compact design so that our PCB can fit into our enclosure nicely. So as you can see, the current sensing and voltage sensing resistors and capacitors shown here on the right. They're 1206 surface mount, and the chip itself is SOIC. All the traces from the PFC controller itself run off to the bottom edge of the board into a female socket. This makes it easy for debugging and to ensure us a specific operation when the board is hooked into the boost circuit board or without it. And on the PCB layout right here, I pulled out a couple of important pins. The pin 1 and pin 2 are 12 volt bias and ground reference respectively. Pin 3 is the instantaneous inductor current sensing pin, which shuts off the controller if it detects an open circuit. Pin 4 is input AC voltage sense, which incorporates brownout protection. Pin 5 is connected to the MOSFET gate, and pin 6 is the output DC voltage sense, which uses a 5 volt reference to activate or deactivate the chip. It's important that all these traces meet up with the boost circuit and make firm contact to ensure proper operation of our power supply. And Arash will be talking about our testing setup.
We have spent the most time of our project on testing. As you can, the recommended testing setup from our graduate advisor is shown here. The Chroma 6590 AC source provides input voltage and current. The output board is connected to the Chroma 63210 electronic load. We used oscilloscope to monitor our waveforms. We used differential voltage probe to monitor input and output voltages. We also used current probe to monitor the input current. When we want to test the board, we need to be extremely cautious because the power supply operates with high voltages and current, and as a result, the power output will be so high. Next, I pass it on Johnny.
Thank you, Arash. So after the testing setup, we have results. Shown here displayed is our current waveform from those results, with the voltage in blue and the current input current is in pink. As you can see that they are in phase with each other. Also measured was the quiescent current under no load conditions. This power converter draws 19.1 milliamps, as well as a load regulation of 0.075%. Also included is the hold-up time, which we surpassed with 10.4 milliseconds, and the ripple on the output is a 9.75 volts peak to peak, as well as a power factor of 0.99. Now also, we compared our board with the Texas Instruments evaluation board, and I put the efficiency versus load curve on the left-hand side, with the TI evaluation board in red, and our board is in the dashed blue. As you can, at the lower and lighter loads, the efficiency is not as great. However, once we reached about half the load, we got an efficiency of 95% for our board. On the right-hand side is the curve for output voltage to inputs. As you can see, the output is linearly correlated with the input until it reaches 90 volts input, where at that point the controller turns on and starts to boost our output to our nominal 400 volts DC after the transient subsides. So in order to quantify our project, I sent it to Omar. He would talk about the budget.
All right, so this is a detailed breakdown of our budget. Each of the prices listed on the right, consider the amount spent on each of the components. Each amount of parts for each component. I'm sorry, it doesn't make sense. So for instance, right here, the MOSFET says $50, but we really spent $50 on 12 MOSFETs, not just one. Vitec Electronics provide us with 4 boost inductors for our testing boards as well as our final board. And our chip was sampled from Texas Instruments, so that was no cost to us. As you can see, our total spent was $480, about $270 below budget, and we probably actually saved a bit more considering what we actually used and spared. Johnny will now talk about management and milestones.
So in order to first get some ideas, we used that Texas Instruments evaluation board, evaluated it, and tried to improve upon it. So what we started out with was a 3-stage PCB design, and this incorporated an EMI filter stage for one PCB. The second PCB held all the power components, and the third PCB had the controller circuitry on it. So after we evaluated this, we just consolidated everything together. So we have our current mother-daughter board PCB configuration. So once we were able to get that working, so it outputs to 400 volts DC, we wanted a way to showcase how this power supply was actually working. So we put together a demonstration load, which is basically 3 strings of light bulbs to act as a resistive load in order to dissipate the 390 watts of power that we will be pushing at it. Also, in order to cool all those components, we designed a heatsink tunneling, which has a fan on the end of the heatsink that will blow 36 CFM of air through that tunnel in order to cool the devices, and it uses the 12-volt DC power bias that we have on board. Once everything was put together, we put it all in an enclosure for design day, and this is our finished product. Once I like to reiterate that we are the first team at San Diego State to design this AC-DC converter, and I would like to open the board up to any questions.